Gödel's incompleteness theorem explained and proved. What Gödel's incompleteness theorem says is if you have a language that includes logic, you can't have a finite list of axioms written in the language that are complete and consistent. Axioms in the language are statements written in the language that you believe to be true in order to figure out other statements in the language that are true. Complete means that any statement written in the language that is either true or false can be proven from these axioms that it is either true or false. And consistent means that every statement that is either true or false can be proven to be either true or false, and its negation, its opposite, will be the opposite Boolean value. So if you have a statement that is true, the opposite of that statement will either be the opposite Boolean value or undecidable, or not have any specific Boolean value. But you can't have a statement and its opposite that have the same Boolean value of truth. And what Gödel's incompleteness theorem says is that if you have a list of axioms that fit all of these constraints, then that's impossible. There's a pretty simple proof for that using the halting problem. So there are many different programs, and you can be sure that for any finite list of axioms, one of these programs will have the ability to have your list of axioms. It will, by chance, be that list of axioms, and it will be able to derive, using that list of axioms, whatever you can derive with that list of axioms. And what that program does is it finds what the prediction of your list of axioms will be for whether the program will halt, meaning stop, or not. So it says that if the list of axioms you have will predict that the program will stop, then the program will continue forever. And if the list of axioms you have will predict that the program will continue forever, then the program will halt. And this program G has a definite value of whether to stop or not, whether to halt or not, because your list of axioms will have to say that the program will either stop or not. And if in your list of axioms you have an option to not answer, you can just write in the program G that if it's undecidable according to your axioms, then the program will have a default value of whether to stop or not. But that the axioms are undecidable of whether G will stop or not, by definition means that they can't answer to the definite value of the halting of program G. So now that we have a definite value, of a definite Boolean value, that our list of axioms, by definition, can't derive, then I can just build a statement, and I'll call A, that says, if program G will halt, and I'm false, I'm false. If program G won't halt and I'm true, I'm false. What does this mean? Well, there are two options. Either program G will halt, or program G won't halt. If program G will halt, and this statement is false, then the statement itself says I'm false. So, if the statement is false, and it says I'm false, then it must be true. But we just said it's false. That causes a logical contradiction. Meaning, if program G will halt, the statement can't be false. It must be true. Otherwise, there'll be a logical contradiction. If program G won't halt, and I'm true, then I'm false. So, if the statement says I'm false, and it's true, then there's also a logical contradiction, because it can't be true and say I'm false. And that means that if program G won't halt, the statement A must be false. So if program G will halt, statement A must be true. If program G won't halt, statement A must be false. So it's either true or false, definitely, and it relies on information that our list of axioms can't get from program G. Therefore, we can't derive from our list of axioms for whether statement A is true or false. This causes our list of axioms to be incomplete. Let's look at statement B. Statement B is just the opposite of statement A, where I'm false changes to I'm true, I'm false changes to I'm true. Well, in statement B, whether program G will halt or not, statement B says I'm true. And when the statement says I'm true, you can't know if it's true or false. It can either be true or false. So, therefore, statement A has a definite value. Statement B doesn't have the same value because it doesn't have any definite value. It's either true or false. And now we just don't care about statement B because we proved that any list of axioms we have must be incomplete using program G. So what we did is we found inaccessible to our list of axioms information in the form of a Boolean value, a definite Boolean value, and we devised a statement A. We created a statement A that uses that definite Boolean value information that can't be accessed from our list of axioms to say whether statement A will be false or not. Therefore, Gödel's incompleteness theorem is true, and for any finite list of axioms in a language that includes logic, isn't complete. Thank you for watching. Please comment and argue with me in the comments.